NANOgrav has found evidence for a gravitational wave background. We believe that this gravitational wave background comes from the cosmic merger history of supermassive black holes. Those are 1 billion times the mass of the sun. This is the first time that any gravitational wave detector has detected gravitational waves from supermassive black holes or any kind of gravitational wave background. We've just opened a new window of measurement for the universe.
Hello, my geeslings. This is Mother Goose Robinson Earhart here with the introduction to Robinson's podcast number 108. And this awesome breaking news episode is with Chiara Mingarelli, who is a gravitational wave astrophysicist and a professor in the Department of Physics at Yale University. So Chiara studies supermassive black holes at the centers of galaxies and their mergers using data about gravitational waves that are detected by pulsar timing array experiments. And this episode is awesome for a number of reasons. One, its release coincides with a massive announcement in astrophysics, the first detection of the gravitational wave background, of which Chiara was a part of. And two, there are few topics as interesting as black holes, gravitational waves, and their ilk. But Chiara and I do two things in this episode, which we incidentally recorded in two parts. So the first is all the background you need to understand this data release. So we talk about pulsar timing arrays, which are sets of very special stars whose rotations can be measured and analyzed to detect gravitational waves. We also then talk naturally about just what gravitational waves are, and then how they're related to black holes, their mergers, and other astrophysical phenomena. And then in the second part of this episode, we talk about the release of NANOgrav's new data and what it tells us about the gravitational wave background and black hole mergers, as well as what's to come with this new era of research and theory. So you might also want to check out Chiara's episode on Sean Carroll's Mindscape, which also provides a lot of really great background information for understanding this new data release. But then you can also keep up with Chiara on Twitter at Dr.C. Mingarelli or on her website at chiaramingarelli.com. And lastly, you know the drill. Likes, comments, follows, subscribes, shares. All those things are endlessly helpful. And now, without any further ado, I hope you enjoyed this conversation as much as I enjoyed having it with Chiara. At this point in the podcast, I've only spoken to one other astrophysicist, Kevin Hang of LMU, and he works on exoplanetary atmospheres. Somewhat similar, I think, to Sarah Seeger. I think their work overlaps. But he told me that there are basically three categories of astrophysicists. There are, for him, there's the instrument builders, the observers, and then the theoreticians. And so here's a somewhat heavy question to start off, but hopefully not too hard to answer. But how was it that you ended up not just in astrophysics, one, but a theoretician, and then within the theoreticians, a specialist in black holes and gravitational waves?
Oh my gosh, that's all the way down the rabbit hole. Okay, so when I was a kid, really loved looking at the night sky. I grew up just outside of Ottawa in Canada in a small town called Rockland, Ontario. And we had really beautiful dark night skies. And I loved to hang out with my friends and play outside and look up at the stars. And, we would try to find UFOs and, scare ourselves and tell each other stories. And so, it was always space was always really fun for me. And it was always very exciting to think about what was out there in terms of exploring. And so, as a child, I was very adventurous. I liked to climb trees and explore the forest behind my house, which was huge. And what was an even bigger challenge than that, right? Space. And so I loved dreaming about space. And in the early 90s, Hubble launched. And then we suddenly started to get all these really beautiful images of nebulae and the planets. And I started putting those posters on my walls, and I saved my babysitting money to buy Scientific American magazines and Discover and Sky and Telescope, anything that had those beautiful glossy images of space. And then one day my dad, who's a mathematician, told me about black holes. He's like, you seem to really like space. Like, what about black holes? And I was like, well, what's a black hole? And, he explained to me it's this kind of star that is, so heavy that light can't escape the gravitational pull of the black hole. What is that? That's not real. Like, you must think that I'm a baby. Like, that's obviously not true. But, when I learned that they're actually real and started thinking about all of the possibilities of, where are they? How near to us are they? Are they close? Are they far? And how big are they? And how do we know if they're black that they're even out there? Right? And all of these, really basic questions. I started, just being really curious about them. And then I was in this very fortunate position where then, a few years later, my dad said, you can have a career studying black holes. And I was like, well, like, now you must think I'm really stupid. And he was like, why would you say that? And I was like, because if you can study black holes for a living, then everyone would be doing it.
Yeah.
He was like, not everyone feels the same way that you feel about black holes. And so I knew that, that was really what I wanted to do. And that curiosity really pushed me through a lot of the schoolwork and, people throwing me curveballs or telling me that I couldn't do it in different ways and form. And, that brought me all the way to my first author paper that I wrote during my PhD that was published in 2012, where I actually did make a discovery about black holes. But discovery in the terms of a theoretical discovery, which means that I took a whole bunch of puzzle pieces and rearranged them in a new way and made a prediction about a new measurement that we could possibly make. And so as a theorist, I came, I think, to the theoretical aspect of it because I really like math. And I've always loved science, and I love just imagining things and thinking about things. And so, but my personal flavor of theory is that I like to make predictions about things that I think could possibly be observed, not just esoteric things, but I like to be as concrete as possible so that if you try to test one of my theories and it doesn't work out, then I can go and adjust it, right? Like, you can go open the hood of your theory, adjust a whole bunch of things and be like, okay, now does it work? And so then you have this feedback with observers, and they're like, no, like, the thing that you thought was there is not there. So something is broken. And then you go back and you try to figure out, like, what part of my framework doesn't work? I have all of these pieces taken from different measurements, and I put them together in this way. So what did I do that was wrong, or what did I not understand? And it's always kind of reconstructing the puzzle to see if all the pieces fit, and then, trying to validate those theoretical predictions with data.
I had a similar experience to you with Hubble, where it just totally lit up my imagination. And when I went into undergrad, I also wanted to be an astrophysicist, at least at one point in time. But I'm curious, because this was my experience, but did you feel at all betrayed when you discovered that most of those images are false light images that don't actually render the celestial objects as we would see them with the naked eye? I mean, they might be taken in X-rays and then just sort of shifted to the visible light spectrum so that we could see what's going on, or we have an idea of what's going on.
Yeah, I didn't feel betrayed. I think it's interesting that you felt betrayed by that. JWST must be a huge betrayal to you as well, or maybe you're over it now. I was more in awe of how clever people are, right? Like, how do you take something that's invisible to my eyes and then help me to see it? And then how can you distinguish that? So, what they typically do is that there's a color scheme that we associate with different wavelengths of light that we can't see. So sometimes you'll think that an X-ray is pink, for example, right? And that'll be like a pink overlay. And so they'll take multiple images and overlay them so that you're seeing all of these different wavelengths that you normally wouldn't see. And I think that it just helps the images be more spectacular and awe-inspiring. And perhaps as a theorist, I have, I'm happy to give a lot of artistic license to the people for the purposes of inspiring awe and that kind of thing. So yeah, I felt totally fine.
Yeah, that's totally fair. Much more charitable than I am, and totally reasonable too. But so in introducing your work, I think we should start with gravitational waves. Now, like we've just been discussing, the celestial objects like black holes and various types of stars, they emit electromagnetic radiation across the spectrum. So X-rays, visible light, radio waves. And each of these sorts of light might tell us something very different about these objects and their interactions with other objects. And I think the general public and my listeners are probably much more familiar with electromagnetic radiation because it's light than they are with gravitational waves, which are fundamentally different. So just what are gravitational waves?
Right. Great question. So gravitational waves are ripples in the fabric of space-time that travel at the speed of light. And so this really goes down to Einstein's theory of gravity, that, gravity is not just some dumb force between two objects with mass, but that it's actually these objects with mass are creating curvature in the fabric of space-time around them. And that curvature is gravity. And so if you have two massive objects that are orbiting each other, they're perturbing the fabric of space-time around them and sending out ripples. And those ripples are very small, but they're measurable. And in fact, the first detection of gravitational waves happened in September 2015, and the announcement came later in 2016. And that was of, two black holes that were roughly 30 times the mass of the sun merging. So these gravitational waves are completely different from light waves. So you call light electromagnetic radiation. That's correct. With gravitational waves, we call it gravitational radiation. So it's a nice analogy. But what really blew my mind when I was starting out studying gravitational waves is that it's a completely different spectrum, and it has nothing to do with light, right? So I think naively, when you first think about it, you want to look at the light spectrum where you have, X-rays, optical rays, radio waves, and be like, where do gravitational waves fit on this? It's its own thing. They are not related to each other. And so at the very high frequency end of the gravitational wave spectrum, you have gravitational waves from stellar mass black hole mergers. So black holes that are, between 10 or a few times the mass of the sun to 10 to maybe 100, but that's about it. And those merge in a frequency range that would be in the human audible range. So if our brains had gravitational wave detectors in them and our ears were gravitational wave detectors, when black holes would merge, you would actually hear a whoop sound at the very end of their life. Like you could actually hear it. It's in the human audible band. So those gravitational waves are very high frequency. The experiment that I work on right now is a very low frequency gravitational wave detector. And so whereas the LIGO detector, which made this first detection back in 2015, is sensitive to gravitational waves that are between maybe 100 and 1,000 hertz. My experiment, which is called pulsar timing arrays, the gravitational waves that we look for are 1 to 100 nanohertz. And so to wrap your mind around what a nanohertz is, right? If you're not used to thinking about hertz, maybe it's more intuitive to think about what would be the orbital period of these black holes. Right? So 1 nanohertz is equivalent to an orbital period of 30 years. So these black holes are very slowly moving and they're very widely separated. But importantly, our black holes in this frequency band are supermassive black holes. Those can be 100 million to 1 billion times more massive than the ones in the LIGO band. So we see a different class of black holes than LIGO does. So LIGO could see black holes that are, a few to 100 solar masses, whereas we see black holes that are, 10 million, 100 million to 1 billion times the mass of the sun. So a completely different class of black hole.
Mm-hmm. And My understanding is that, sorry, the cat, her name is Pins. She's known as the podcat now. She's a
The
she's
per
a
what
co-host
my
of the
dog?
podcast. Huh?
I have a dog here too.
Oh
I,
yeah. Well,
I have Coco Bean the love machine.
does he want to be part of the podcast for a moment?
I think she does.
She does.
Snugglebun, come here. Come here. What a good girl. Come here.
Snugglebun's a good one.
Oh, yes. Oh, yes. I know. She was sleeping. Oh,
Is that a Frenchie?
yes.
Oh, very cute. My dog's on the bed. He's at Vizsla. He's just loafing. But your Snugglebun is very cute.
Thank you. That's Coco.
Now,
Go back to
returning to astrophysics.
yeah.
My understanding is that observing and measuring gravitational waves pose unique challenges for astrophysicists because they aren't light. You don't use telescopes or radio antennae to detect them. So you already mentioned the pulsar timing arrays and LIGO, and my understanding is that when LIGO first detected gravitational waves, it was a huge moment in astrophysics. So just how are gravitational waves captured, so to speak? What sort of equipment, or what? Well, let's start with LIGO. How does LIGO work?
So LIGO works by, it uses the fact that light always travels at the speed of light. This is the fundamental fact. So it can serve as a pretty interesting ruler. So what happens with LIGO is that you have a laser beam that hits a beam splitter, and it splits the beam into two beams. And those beams propagate at 90 degrees to each other. So each beam goes down an arm of this detector and then hits a mirror and bounces back. When the beam bounces back, it interferes with itself destructively, and so you see no light. So the peaks and the troughs cancel each other out and you see nothing. Because the arms are exactly, the right length so that when they recombine, you don't see any light. Now, gravitational waves change the distances between objects. And so if a gravitational wave were to wash over the LIGO detector, what happens is that one arm gets a little bit longer and the other one gets shorter. And so now that destructive interference pattern is no longer destructive, you can start to see light. Whereas if the arms were the exact same length, you wouldn't see any light. And so one gets longer as the other one gets shorter, and then vice versa. And it makes this, it does the LIGO dance, where one gets longer, the other one gets shorter. And as the black holes merge, this happens faster and faster and faster and faster. And then you get the whoop, and at the whoop part, then they merge. So that's how LIGO works. It really focuses on the fact that gravitational waves change the distances between objects. And so one detector arm is getting compressed and the other one is getting stretched. And then the same thing happens back and forth, and you do the LIGO dance. So pulsar timing arrays are really unique and I think a brilliant experiment, because if you now think about gravitational waves that have frequencies of 100 nanohertz, or their wavelengths are of the orders of 15 to 30 years, you can't just, you need a huge detector where the wavelength can, fit in that detector, right? So you'd have to build a detector that had, arms that are light years long, but you can't do that. And so we had to look in nature. And there was this brilliant idea that came out in the late 70s and the early 80s, where you could use the fact that pulsars are very stable clocks in our galaxies. So pulsars are these neutron stars, and their spin axis is misaligned with the magnetic field line. So every time it spins around, it sends a flash of radio waves towards the Earth. And it's so regular that you can set your watch to them. They used to be better than atomic clocks at timekeeping. And in 2012, atomic clocks got better. But right now, these pulsars there's a special class of ultra-stable pulsar called the millisecond pulsar that's so good at timing that you can time down to 100 nanoseconds over a decade. So that kind of experiment is required if you're trying to find these very small space-time perturbations. So then applying the similar idea, you can turn the whole galaxy into a gravitational wave detector by using these pulsars. Because now you have these ultra low frequency gravitational waves washing through the galaxy, right? Stretching and squashing things, but instead of it happening, 100 times a second or 1,000 times a second, it happens, once every 15 years or once every 30 years. And so what happens is that the gravitational waves change the distance between the Earth and the pulsar. And so the pulsar spins, right? Those radio flashes arrive a little bit early and then a little bit late, and then a little bit early and then a little bit late. And so this is happening not only in one pulsar, but it's happening in all of the pulsars in our galaxy. And with the collaboration that I'm a member of, NANOgrav, we currently have about 60 pulsars where we're doing this kind of experiment, looking for changes in the arrival times of these flashes from pulsars to try to understand how the space-time is changing between us and the pulsars.
Mm-hmm. Now, so not that the PTAs aren't extraordinarily interesting, and we'll return back to them, but for the moment, restricting ourselves to LIGO. So at any given moment, the universe is so huge, there are countless binary black holes merging. So what I have in mind is there just has to be so much noise going on in the universe. How is it that with LIGO, like this one crucial experiment that we were talking about, the researchers are able to pinpoint that it is precisely this pair of black holes that is having this effect on the two beams of light?
Yeah, so that's a great question.
And there's an analogous question for the pulsars as well.
Yeah, there's a few layers to get to answer your question. So number one, yes, there's lots of events that are happening, but only events that are loud enough or strong enough in terms of their gravitational wave emission can be detected by the LIGO detectors. And then number two, how can you tell where the signal is coming from? So the best way is to have at least 3 gravitational wave detectors. So there's LIGO, and there's Virgo, and there's CAGRA in Japan. And while it's, still a bit aspirational to have them all working at the same sensitivity at the same time, there's typically, a very solid network of the 2 LIGO detectors plus the Virgo detector that are on and can operate at the same time. And with those 3 gravitational wave detectors, you can triangulate where the signal is coming from in the sky. And so then it gets a little bit easier to tell where it comes from. However, it's very difficult to pinpoint anything, because when 2 black holes merge, it's not a given that there's going to be gas or dust surrounding it that would make an electromagnetic flare or observation, right? And so looking for something like a gamma ray emission that's happening at the same time as your gravitational wave emission is really difficult. But, we're looking forward to doing this a lot more in the future. It's something that we call multi-messenger astronomy, where you have not only gravitational waves, but you have gravitational waves and light waves, and potentially things like neutrinos, which are all
the counterparts.
Of course, exactly. And they're all independent measurements, and they can tell you different things about the system. So gravitational waves are amazing because the signal is so clean, right? If your gravitational wave source, these 2 black holes that are merging, are perturbing the fabric of space-time itself, you don't have to worry about gas and dust, right? It's not like you can put your telescope at it and be like, oh no, there's this huge gas cloud in front of what I want to see. Gravitational waves don't care about that, right? They are moving space-time itself. You can get very clean signals that come from those systems.
They sound in a way almost like neutrinos, in the sense that, neutrinos are so tiny that they really don't interfere with much. So, they pass deep into the Earth.
That's right. Neutrinos are amazing, right? The fact that one neutrino is all neutrinos and all of that stuff has always blown my mind. When I was an undergraduate, I actually visited the Sudbury Neutrino Observatory, and I saw the experiment. It was called SNOW, and it was absolutely amazing. It was 2 kilometers underground.
Yeah, well, maybe since we're talking about neutrinos, I mean, it's a bit of a digression. You could say more about what they are, and then when you say the fact that one neutrino is all neutrinos, that is that like a generally agreed upon fact, or just one way of parsing the theory?
Right. So, I mean, first of all, I am not a neutrino physicist or a particle physicist or an astroparticle physicist, but I'll tell you what I know
Okay,
regardless
sure,
of how
sure.
limited it is about neutrinos. So I think that the easiest thing to focus on is the sun. So the sun has a lot of nuclear reactions that are happening in it, and those reactions can create neutrinos. And so the first neutrino detectors built were looking for a very special kind of neutrino. I believe it was the electron neutrino, but I'm sure my colleagues will all email me and correct me when they hear me say the wrong thing. But anyhow, what you need to know is that, there were these 3 types of neutrinos that exist in nature, theoretically, and that the sun should only produce one of them. And what they found when they built these detectors is that they were only really observing about a third of the neutrinos that they should be. And so what's wrong? Is it that the detector's not working? Is it that other things are happening in the sun? Like, what's happening? So there was this theory that neutrinos can oscillate. And so your electron neutrino can become a tau neutrino, can become a muon neutrino. They can all alternate between each other. There's this mixing that happens between them. And then at SNO, they played a key part in solving what was called the solar neutrino problem, because they made a detector that could detect all of these different kinds of neutrinos. And in fact, then they found all of the solar neutrinos. They were all there. They were just all the different kinds of neutrinos were there. It wasn't just one that they found, but it was all of them. So even though the sun produced a certain kind of neutrino, because neutrinos can all oscillate between these 3 different kinds of neutrinos, then you had to build a detector that could find all 3 and not just the one. And so this happens because neutrinos have a very small amount of mass. And so the Nobel Prize is actually awarded to this discovery just a few years ago. So Arthur McDonald at Queen's University was, one of the pioneers in this Sudbury Neutrino Observatory experiment that actually solved the solar neutrino problem. So, Canadian hero.
Yeah, and your colleagues might rush to correct me as well. But what I recall about neutrinos, I mean, one, they're so fascinating because they're so tiny. There are billions of them moving through you at any given moment, but not interacting with you at all. And they're caused by these very high energy events in the core of the sun. But the experiments that initially detected them were, I'm thinking of one, maybe it's SNO, I don't recall, but deep in like some Italian mine where they had this big vat of deuterium, and you would sort of just like set up this detector and you would detect these rare blips where a neutrino occasionally knocked into one of these atoms of heavy water, these molecules of heavy water.
Yeah, that's right. So, so Gran Sasso, I think, is the experiment in Italy. And then there's Super Kamiokande or Hyper Kamiokande in Japan. So SNO is definitely not the only game in town. It's just the one that I've seen that looked like an episode of the X-Files. So that's the one that I, really bonded with when I was an undergrad. But yeah, something like 8 neutrinos is a non-trivial event. Like, finding 8 neutrinos is amazing. So I remember going down into like the mine, because where I went, it was an active mine. And the miners were like, "Did you find any neutrinos today?" And I was like, I don't know.
Yeah, that's funny. Okay, back though to your area of expertise. So that's interesting. So there are 3 gravitational wave observers now, like LIGO, but then there are also 3 PTAs. So there's one in North America, one in Europe, one in Australia, and
There's actually
you mentioned that
now as well.
Oh, so there's 4 now. Okay, and you also mentioned that there are, I think, 60 pulsars that are being observed at the moment?
So it's a slight subtlety. So there's around 60 that are being observed in North America, similarly in Europe, but we have some of the same pulsars that we observe. And in the southern hemisphere, they can see different pulsars than we see in the northern hemisphere. So together, we actually all share data under this collaboration called the International Pulsar Timing Array. So that's when Europe, Australia, India, NANOgrav, which is where I'm at. And then also there's a new experiment called Meerkat, which is in South Africa. And this is a Pathfinder experiment for the Square Kilometer Array. We all share data, and one of my postdoctoral researchers is combining all of this data to make a super data set, which has information from all of these pulsars. So that one will eventually have 85 pulsars. So everyone has a slightly different number of pulsars, but some of those overlap, right? So the North American experiments will see many of the same pulsars, and the Parkes Pulsar Timing Array in the Southern Hemisphere will see largely, a completely complementary set of pulsars.
Well, okay. I think we have a good background now on the gravitational waves. So, but before we turn to the astrophysics of black holes, and maybe this harkens back to those false light images I was asking you about, but I have what's perhaps more of a psychological and less of an astrophysical question. But how do you see black holes in your mind's eye? So I'm asking, the objects themselves, if I understand correctly, are of extremely, extremely large mass, but essentially infinitesimal size at their core. And of course, there's no light within the event horizon of a black hole to perceive. So do you see in your mind's eye like something point-like and kind of seething, or something massive and rippling that might correspond to the event horizon, like warping light all around it? Or what is it that you're envisioning when you think about black holes?
Okay, so I'll walk you through my imagination approaching a supermassive black hole. So the first thing that I think everyone should know about supermassive black holes is that, like, black holes are like dogs. The small ones are like really tiny and yappy and can bite you and hurt you. So if you get close to a small black hole that's a few times the mass of the sun, if you get close to the event horizon, it'll start to spaghettify you, right? And like shred you, because there's something called the tidal disruption radius. And that's where this spaghettification, which is actually a technical term, happens, right? With a supermassive black hole, that spaghettification happens inside the event horizon. So you could actually be, in your spacesuit, taking a walk outside and accidentally cross the event horizon of this black hole and still be in one piece, right? So like the big ones are nice and kind of fluffy, and you don't really have to worry about them. And the small ones are where you'll get like instantly, well, not instantly, but at the event horizon, you get spaghettified. And so it would be very difficult for you as an observer to cross through and actually like look inside and see what's happening. It doesn't mean that you can ever come back and tell anyone what you see, but it means that at least you could cross over into the black hole inside the event horizon and actually look around for a little bit and see what's happening before you eventually die.
Is it because I don't know what the technical word would be, but the gradient or the shift of the gravitational force, it sort of gets stronger much more quickly because of the
I think your intuition is right. It's the curvature.
Okay. Exactly. Okay.
Yeah, exactly. So it's the curvature of space-time that's, supermassive black holes are so big that you have a more gentle gradient at
Perfect.
first,
Yeah.
right? Whereas with the smaller ones, you're like, bam, right into the black hole. So yeah, that's exactly right. It's this curvature argument. So, but of course, this is all assuming that there's nothing else around the black hole. In reality, supermassive black holes are in the centers of massive galaxies, and there's lots of stuff happening there. So these supermassive black holes can have disks of material around them that are superheated. And so if you've seen the movie Interstellar, you've probably seen what's become, I think, this iconic image of a supermassive black hole that has this accretion disk around it, the eyebrow on top of it. So fun fact about that eyebrow is actually the back of the accretion disk. So if you imagine, like my head is the black hole and the accretion disk is around it, because there's so much curvature in the space-time, it allows you to see behind.
It's gravitational lensing.
Exactly. It's showing you what's behind the black hole viewed at a certain angle with the camera. And so that's a cool fun fact.
Yeah, and those, I think, gravitational lensing, again, you can correct me if I'm wrong, that was a crucial experiment for supporting some of Einstein's theories, that you could look at a star. I don't know if it was originally performed with the black hole or with
the sun.
Okay, yeah, the sun. You could see stars that were behind the sun, but because the light it travels this, I don't know if I'm using the word geodesic correctly, but this path around the sun.
Yeah, that's right. So it happened during a solar eclipse, because that's the only time where you can see the stars that are close to the sun, right? And so if the sun is being eclipsed, then you can actually start to see the fainter light. And so you can see, where the stars should be, and you measure where they actually are. And then that light deflection tells you that actually, yes, the sun is curving space-time around it. And the position that you see of the stars is slightly deflected because of that curvature. So back to the black hole. So now you're, close to the supermassive black hole. And let's just imagine that you're Mario and you are in one of your indestructible, suits where nothing can harm you. You've had one of those star power-up things, right? And you're
okay. I was wondering where Mario was coming into
exactly.
this.
So let's just pretend that it doesn't matter, that there's X-rays coming at you, ultraviolet rays, that it's hot, that, basically if you look at it, you'll die. Just ignore all of that. And now you can cross into the event horizon of the black hole. What's inside is really anyone's guess. But formally, what we do know, just by looking at the map, is that the space and time coordinates flip. It's really hard to understand what that means in a physical sense, right? But it's true. It happens. And also, if you're crossing through, your own clock and your brain and your perception of reality keeps going normally. But if someone were watching you cross into this black hole, they would never actually see you disappear into it. You would just kind of get slower and slower and slower as you got closer to the event horizon, but they would never actually see you cross through it. So for this external observer watching you, you never cross. But you, as the explorer, you just go through and you just keep going on and looking around you. So it's really incredible. This is all relativity, right? Everything just depends on your point of view, and observers can, perceive things happening at different times, and space and time and gravity is all really intrinsically intertwined in this. And so inside the black hole, what I imagine you'll see is, formally, you can't see the singularity, because the singularity you can only see it when you hit it. But imagine that there's some sort of core, right? It's probably some quark gluon plasma, some sort of very exotic material. And that can definitely have light that comes out of it. That's entirely possible, that inside the event horizon of a black hole, there's light that's traveling, and it's coming out of this central object, however you describe it, but water coming out of a water fountain, where the light can come out and it goes up to the event horizon, but then falls back down, right? Because the light can't escape. Or maybe some of it kind of goes around and traces a line around. So the light can really be traveling all over the inside of the black hole. So it could actually look like the 4th of July on the inside of one of these supermassive black holes. The disappointing part is that, according to what we know right now, we will never be able to know or to tell anyone what happens. Even if you and I decide to take a picnic inside the event horizon of a supermassive black hole, we can never tell anyone what we see, because we can't get information back out of the black hole.
What's interesting is that was not how I envisioned things. I thought that the gravity, I mean, it gets even stronger within the event horizon. And so no light even leaves this core. It would just be sort of pinned to it, in a sense, by the really strong gravity at this kernel of the black hole.
Yeah, but the point of no return for light is the event horizon. And that's why it looks black, because that's, light can reach that point, but then comes back in on itself.
I see. That makes sense. And maybe then you've already answered this question, but so is this how you think of the black hole in your head then, essentially, as this perhaps 4th of July like thing trapped inside this black ball that we can't get inside of?
Exactly. Yeah, that's really what I think of, but that could be totally wrong.
Yeah. Granted that's fine. And now, how then, going back to where we started, how do black holes produce gravitational waves? And then what are the counterparts that we also already alluded to in the electromagnetic radiation spectrum that correlate or correspond to these gravitational waves, the process that produces them?
Right. So the first question was, how do black holes make gravitational waves? Okay, so you can make gravitational waves really from accelerating masses. If you have two things that have mass that are orbiting each other, you can make gravitational waves. They're just going to be very weak and undetectable. So like even me doing this, right? Like that makes gravitational waves, but it doesn't mean that LIGO or pulsar timing arrays are going to see them. So you have to have objects that are very massive that create these. And so the strength of your gravitational wave correlates very strongly with mass. So the more massive objects you have, the stronger your gravitational waves. And the orbital frequency is also really important. So as the black holes get closer and closer together, they produce really strong gravitational waves. So what's special about black holes is that they're very massive and they can get very close to each other without ripping each other apart. And so you can create very strong signals. If you were to, example, have two stars, right, even though those stars can be 10 times the mass of the sun, when they get close to each other, their atmospheres will touch and they'll start, disrupting each other, and they can destroy each other, or maybe even create a new star eventually, or perhaps a neutron star. There are lots of things that can happen. But you can't get them into like that final super tight orbital phase where they're creating really strong gravitational waves because they've destroyed each other before they ever get there. And so black holes are really important because they can be very massive and they can get very, very close to each other and make those very powerful gravitational waves. So as the black holes are orbiting each other, they're really creating these ripples in the fabric of space-time. And you can imagine that as, you're floating in the ocean and you start splashing around and you make waves. Those black holes are really splashing around in the fabric of space-time, and the waves propagate out in all directions.
And I think now enters a really important concept for your work. And I think this is where the PTAs come in, and gravitational waves in this 1 to 100 nanohertz frequency. And that is the stochastic gravitational wave background, which is sort of the constant background frequency of the universe in gravitational waves. So what is this, and why is this so important for what's going on in your black hole research?
Right. So that's a great question. At the very high frequency end where LIGO lives, and, it detects the last final fraction of a second of a black hole merger, right? Whoop. And then that's it. So at very low frequency...
Oh, really? The last second?
The fraction of a second, maybe like 0.4 seconds. Yeah, if you get something more than a second, it's exceptional and probably a binary neutron star and not binary black holes. But this is a topic for another time. But yeah, LIGO will see the last fraction of a second of a binary black hole merger. Pulsar timing arrays can detect gravitational waves from supermassive black holes. And supermassive black holes create such big gravitational waves that you can start detecting them 25 million years before the black holes merge. And so those, are detectable for a very long time. So these supermassive black holes live in the centers of galaxies. And when the galaxies merge, the central supermassive black holes start to merge. And so the pulsar timing array supermassive black hole mergers are very rare, right? Because you need a whole galaxy merger to happen to create one event. But that event takes so long, right? That 25 million years is a very long time that chances are somewhere else, there's another galaxy merger happening with its own pair of supermassive black holes that gets to the center, and then they start to merge. And then somewhere else this happens. And then somewhere else this happens. And so over 25 million years, you can have a lot of overlapping gravitational wave signals from these supermassive black hole binary systems. And that overlap creates a gravitational wave background. So you said the word stochastic earlier. That just means that it's a random gravitational wave background.
And you mentioned this 25 million year time span. And so this science is particularly interesting because unlike experiments on Earth that might take place in like seconds, minutes, or even weeks, we're dealing here with events that do not take place on human timescales, which means that we have to go about investigating them in completely different ways. And am I correct then that because of this sort of timescale limitation and the indirect way we're going about studying them, that much of our knowledge of black holes and their mergers remains like quite hypothetical?
Hypothetical is one way of saying it. I would also say that it's right now it's very, theoretically driven, that we're in search of the first observations of this, and that the first observations will really help us to understand the timescales of these supermassive black hole mergers, and also if there's anything else interacting with the black holes. But for example, the way that we think that black holes merge at a very fundamental level is that they're orbiting each other, they release energy in gravitational waves, and then the orbit shrinks in response to this energy loss. And then the closer they get together, the faster they lose energy, and it's a runaway effect, and then they merge. A runaway effect, of course, over 25 million years. So everything is very slow when you're talking about galaxy evolution and black hole evolution. And so the point is that these things take a really long time, and they spend so much time emitting gravitational waves that there's this, something like 100,000 to 1 million sources at any particular frequency. And you can't disentangle them anymore when there's that many sources in one of those frequency bins in your detector. And so that's why we think that there's this random background. But eventually, when we do measure this background, we'll be able to tell if there's gas and stars that are interacting with the black hole, because those gas and stars will change the orbital evolution that we measure. And if this is happening with, the cosmic merger history of black holes, the way that the amplitude of the gravitational wave background evolves as a function of frequency will change. So it won't be a straight line like what we imagine for just gravitational waves, but there's going to be another shape that we can detect in what we call the strain spectrum. But this is really just to say that the behavior of the amplitude of the gravitational wave background as a function of frequency will change. It won't be what we expect.
Is the gravitational wave background in this way analogous at all to the cosmic microwave background?
So the main analogy between the cosmic microwave background and the gravitational wave background is that they're backgrounds, but they're really completely different. So the gravitational wave background, we believe, comes from this superposition of gravitational wave signals from supermassive black hole binaries, and that you build that up like one source at a time, one gravitational wave source at a time, and eventually there's so many that you get a background, and so that it's astrophysical. The CMB, the cosmic microwave background, it's this leftover radiation from the Big Bang that was blown up You can see it like, after, it looks the same mostly in all directions. The differences in, like where it looks different can tell you things about how the universe works and our, cosmological models. And you don't really have to get into that, but it's totally different. First of all, it's light. And it's 3 degrees Kelvin, so 3 degrees above absolute zero. And there are these leftover photons, from after the Big Bang, from when photons could decouple from this primordial soup that it was all trapped in, right? So gravitational waves are different from light. The CMB is based on these very old, cold photons, and the gravitational wave background is based on a superposition of gravitational waves that likely come from supermassive black hole mergers. And so there's different sources, different kinds of radiation. The only thing that's really common between them is the fact that they're backgrounds. So it's a similar idea that you have this, superposition of signals that generate something called a background.
So the gravitational wave background is constantly being regenerated. It's much more current rather than the cosmic background.
Absolutely. Yes, exactly. That's a really interesting way of thinking about it. It's much more dynamic.
And returning to the PTAs briefly, how do you determine which neutron stars or which of the now 4 PTAs to use in any given situation? Or do you attempt to use multiple pairs of pulsars, multiple PTAs for any given investigation of a binary black hole pair just to get a statistically more reliable result?
Yeah, that's a great question. So right now, we're really at the beginning of this kind of global scale coordination. So right now, each pulsar timing array experiment is funded by like the local government. And so, in the US, we have the National Science Foundation, but in Europe, it's the European Research Council. And in Australia, they have their own research council. So is true in India. And so right now, the most common thing to do is for each pulsar timing array to, time their pulsars and to do their science. And then we all get together and say, I've got this data set for this pulsar and I can combine it with your data set with that. And we start trading data. And then people like my postdoc, Deborah, come in and they combine the data sets to make these super data sets, right? So you can imagine something like, there's a pulsar that we see in the Northern Hemisphere, and we have this time series of data that were taken by telescopes in the US, right? So the Green Bank telescope, for example. Now, someone in Europe might be timing it with a European telescope, like Lovell or the Sardinia radio telescope, and they have their own time series of data from that same pulsar. And so now it's a huge task to take those data streams and combine them, right? To stitch them together to make the super data stream. But that's really going to be the way of the future. If you think about the detection statistics, which you touched on in your question, for the gravitational wave background, our signal improves as the square root of time, but as the number of pulsars. So we always want to add more pulsars. We'll eventually get better in time, but not as quickly as we will when we add more pulsars. So what we really want to do is have the biggest number of pulsars possible.
As I was reading some of the articles that you sent me before we talked, it looked like 5 years and then 10 years were particularly important for your accretion of data and testing and research going forward. Why are these times so important? Is it just the accumulation of more pulsars and more data?
So let's see. The truth is that I think 5-year chunks of time are manageable for our brains. That's kind of like the near term is 5 years, and then 10 years is longer term. And so it might, for example, take us a few more, like maybe up to 5 years more data to really fully understand what is creating a gravitational wave background signal. So right now we have, potentially this signal that could perhaps be a gravitational wave background signal, but we're not sure. And so we think that we need some more data to really confirm what this is. And so 5 years is a safe number. It just means that it will happen soon. And 10 years means it will happen in the future. But we're not, but that could be 7 years, it could be 8 years. So really, with these experiments, the timescales are so long that it's hard to be more precise than that, right? Right now, NANOgrav is about to release its 15-year data set. And so it had a 5-year data set, and it had a 9-year data set, and then an 11-year data set, and a 12.5-year data set, and now the 15-year data set is coming out. And so it's always, with these experiments that have very long timescales, you think about the near term in terms of 5 years, and then long term is like 10 years. But, with more data, we can tell definitively what's sourcing the gravitational wave background. Is it really supermassive black holes, or is it something else? We also need to do a really careful job in defining what the noise looks like in our pulsars. So with other experiments, you can turn them on and off again, right? But we can't turn off pulsars and turn them on again. And we also just have like one data set. Like our data set is 15 years long. So we also don't have lots of little tiny data sets where we can go look at our signal and then come back, because we need the whole data set to find a signal. So we have to be very, very careful with those kinds of details as well.
Well, at this point in the conversation, I just have some sort of lingering questions about things that have come up in the conversation that were sort of taken for granted because I didn't want to interrupt. But one is, why is it that black holes tend to anchor galaxies at their cores?
Mm-hmm. So black holes don't actually anchor the galaxies at their cores. In fact, supermassive black holes live at the centers of the galaxies because that's where like the most material is. So they fall to the center. But you can have a supermassive black hole be ejected from a galaxy, and that's something that absolutely can happen. So there
are just rogue black holes floating around through
absolutely
space.
Yes. That's very possible. In fact, I think that one was discovered not too long ago. It was a supermassive black hole with a stream of stars coming out from the back of it. So it has a nuclear star cluster, and it was like, it's leaving this trail of stars behind it as it was traveling through space. So yeah, in fact, no one really knows how supermassive black holes form. It's called supermassive black hole seed theory. And, so there's several competing theories. One is that you have these enormous gas clouds that fragment and form stars, and those stars form black holes, and then those quickly merge into a supermassive black hole. And another theory is that you just get the direct collapse of this gas cloud into a supermassive black hole, and that those supermassive black holes then go and find galaxies, and then they evolve together. But it's not like they can't exist without each other.
And then the next black hole adjacent question I had was why they and maybe it's not often, maybe I'm wrong to use this word, but why they form binaries that orbit one another. So one thing I imagine is possible is that, for instance, if our solar system had initially the mass had been distributed differently, we might have had two stars that orbited one another as the solar system formed. Like, I don't know, maybe Jupiter could have been a star, for all I know. But I also have the sense that, like magnets, stars in different solar systems can form black holes and then sort of start to orbit one another. So are there multiple ways in which black holes will form these pairs and start to orbit one another? Or what is the general way in which this happens?
Yes. So my brain is bursting with a gazillion answers. Let me try to collate them. So yes. So number one, most stars do form in pairs. In order for those stars to become black holes at the end of their lives, they have to be very massive. So more than, 30 or 40 times the mass of the sun. So when they go supernova at the end of their lives, they can form a black hole, but they don't necessarily form black holes at the same time. So what can happen is that you can have a star that's in an orbit with a black hole, and that sometimes some of the gas from that star falls into the black hole, and the black hole can create jets, and then you can, see the system from really far away. So that gas from the star can also form one of these, small accretion disks around the black hole. And in fact, Cygnus X1, which was, I think, the first candidate black hole in our own galaxy, was found through, this kind of technique of looking at X-rays that came from the superheated gas, because you had a star that was orbiting, nothing, right? And that was the black hole that was causing that. So what can happen then at the end of the star's life is that it can also become a black hole if it doesn't, lose a lot of material. And then you have two black holes. And then over time, those will slowly merge and form a new black hole that just has, the first mass plus the second mass minus 5% of gravitational wave energy, because E equals mc squared. So that's one way of forming them. But in fact, you can have black holes that form through very dynamical scenarios. So around our galaxy, we have these things called globular clusters. And there's like this loose collection of stars and potentially and some neutron stars and potentially some black holes. And there it's very dynamic. So there you can have black holes that are being captured and slingshotted. And then you can have very random encounters where you can have something like a head-on collision of two black holes, or you can have a very short timescale evolution. And you can actually tell, we believe, what the formation path was of these black holes by looking at their spins. So with LIGO, you can tell from the gravitational wave signature what the spins are of the black holes. And so if the spins are aligned of the black holes, it means that they probably formed through the first scenario, right? They were both stars, they co-evolved, they eventually merged, and their spins are aligned. But if they're forming in these very dynamic environments, the chances are that one's going to have a spin that's that has nothing to do with the spin of the other one. Their spins are completely, misaligned. And so by looking at things like spins in the gravitational waveform that you detect with your detector, you can, have strong evidence for the history of that, pair of black holes and where they came from.
Well, I have a question about the first scenario that we talked about. So you said that most stars form in binaries. And I think most people imagine, and hopefully we can dispel this if I'm right, that if a star becomes a black hole, it just immediately sucks in everything around it. But my understanding is that if one of these stars becomes a black hole, its mass remains stable, and its mass is going to be the driver of the gravitational force it exerts on everything around it. So if they're already stably orbiting one another, the fact that one of the stars becomes a black hole isn't going to have any effect necessarily on the other star. So it can go about its merry way for another few million years or however long it takes until it too goes black hole. Is that correct?
That's right. Yes, that's
okay.
Absolutely right.
Okay, great.
And in fact, I think a really intuitive example of exactly this is if you were to take the sun and turn it into a black hole with the exact same mass, nothing would change in our solar system. It would just get really cold.
Yeah, exactly. Really cold and dark.
Yeah, the dynamics in our solar system wouldn't change. So you're exactly right. The most important thing is the mass. And that's really the driver of everything.
Yeah, I think that's the biggest misconception people have about black holes. I was the Earth could conceivably, if it became dense enough, be a black hole, and we could just the moon would just continue orbiting about it happily.
Mm-hmm. Yeah, that's right. The most important thing is the mass. Mm-hmm. That's exactly right.
Great. And then what sorts of hypotheses about how black holes merge and their behavior otherwise are you currently contemplating and expecting to have supported or unsupported one way or the other, depending on the upcoming PTA data?
Mm-hmm. So one of the things that I'm known for in my research is predicting the level of anisotropy in the gravitational wave
I saw that word. I liked it.
So anisotropy just means that, that the power in gravitational waves can come from different parts of the sky. So if the sky is isotropic, it looks the same in all directions, right? But given the fact that supermassive black holes, like the background is formed from like 1 and then 2 and then 10 and then 100 and then 15,000, means that there could be some parts of the sky which have more gravitational wave power or hotspots than other parts of the sky, right? And so I was the first person to write a paper on this back in 2013 saying, I'm not sure that this paper from 30 years ago was right when it assumed that everything looked the same in all directions. What happens if it doesn't, and how can we search for this? So I'm very excited to see, in terms of the data analysis, when we can first start to detect anisotropy in the gravitational wave background. I'm also really interested in understanding if some computer models which show that supermassive black hole binaries, now we're talking about the individual systems, can create optical periodic light curves that come out of very bright galaxies. So some galaxies have these, optically varying light curves, and simulations show that those can come from merging supermassive black holes. And so what one of my students is working on right now is actually trying to do targeted gravitational wave searches in the top candidates of these galaxies that could potentially host individual supermassive black hole binary systems. So my take on this is that the first thing that we'll do is detect the gravitational wave background, and that will probably be largely isotropic, as in, to a very high degree, it likely does look the same in all directions. But once we get enough data, we can start to look at something like the cosmic microwave background and see the potholes and the hot spots and get the fine structure of it. And that should let us know, where we expect to find more supermassive black hole binaries or fewer of them. And then we can start to look for the individual ones. But it's not really clear what the order of that will be, because if there's a really nearby pair of black holes that are merging, then we might spot that first before we can spot the anisotropy in the gravitational wave background or fully characterize the gravitational wave background.
And that, again, is just another big difference from the cosmic microwave background, which is just uniform everywhere.
Well, to a large degree it is, but there's a lot of physics that you can extract from the anisotropy in the cosmic microwave background. So there's also anisotropies there. Yeah.
Okay, so I'm totally wrong. I'm glad that you
corrected me. It's more just, it's the way that it formed, right? So because the gravitational wave background, as you put it earlier, is very dynamic, right? That we do have sources that contribute to it that can be close by. They're not all really far away. And so it's distinct from these more cosmological backgrounds.
Okay, well, there were two last threads that I wanted to pull at. And one is, when we first started talking about gravitational waves, you mentioned, I think, that they're closely related to Einstein's theories of relativity. And I saw that you might be able to use PTAs to further test Einstein's theory of general relativity. How would this work?
So when Einstein predicted the existence of gravitational waves, he found that there are two polarizations, just like light waves. Light is polarized, gravitational waves are polarized. There are some extensions to general relativity that propose additional polarizations. And so that will change the way that the cross-correlation patterns that we use to search for the gravitational wave background. So right now, when we search for the background, we take all these data streams and we cross-correlate them with each other. And we look for a signal that's present in all of the pulsars. So the noise in the pulsar should be independent, but the signal from the gravitational wave background should be manifesting in all of the pulsars. And so you look for the common thread that exists in all of these pulsars. And the only common thing that should exist is the gravitational wave background, right? There's no other way that there's some sort of force that's tying together all of these pulsars that's imprinting a signal in it if it's not, this gravitational wave signal. It would be very difficult to imagine what such a signal would be or where it came from. And so by doing this cross-correlation analysis, we can dig out the gravitational wave background signal from all of these pulsars. Now, that signal has two parts. Number one is the amplitude of the gravitational wave background, and that's really set by the astrophysics of how the supermassive black holes merge. And then the other part is this correlation function. It's called the Hellings and Downs curve, but I don't think that is going to change your life at all. This correlation function modulates, it shows you how the amplitude of the gravitational wave background is modulated as a function of the angles that separate the pulsars. So if your pulsars are separated by a small degree, your background amplitude will be a little bit boosted. If they're separated by a larger degree, there'll be less correlation. And so it just tells you how the angle that separates the pulsars is related to the modulation of the amplitude of the background. And it kind of looks like the Big Dipper, or like a sine or cosine wave that like goes down and then only comes halfway back up again. But anyhow, that signature is modified for different theories of gravity. And so when we eventually do detect the gravitational wave background, we can look for those alternative signatures that should be imprinted in the cross-correlated data.
And then that will inform the theory of gravity that we adopt. Okay, great. All right. Well, this is the last question I have, and it's one that I've been looking most forward to, because when I was doing my reading, I came across an exotic species of entity that I don't think I've heard before, and that's the cosmic string, which can also produce, I saw, low frequency gravitational waves that I'm guessing then are detectable by the PTAs. So I've never heard of these before. What are cosmic strings and how do the PTAs relate to them? What's going on here?
So you haven't seen enough Star Trek is the answer.
Yeah, I've watched the newer Star Trek movies, and my favorite movies are anything that has to do with space. But I haven't watched the old TV shows because the special effects just aren't good enough for me.
Oh, ouch. There is a Cosmic Strings episode, although I think when I first saw it, it was already in reruns and I was too young to actually know what they were. Cosmic strings are really fascinating and exotic, potentially like physical objects. So the best way that I've heard of to imagine cosmic strings is that if you take an ice cube and drop it into a glass of water, your ice cube can fracture, right? And that kind of fracture can happen in the early universe. And that's how you can make these cosmic strings. It's one way that you can make these cosmic strings. They're these like infinitesimally small, dense strings, like pieces of spaghetti, right? That don't necessarily have any structure. They're very small and long, and they can form networks with each other from all of these cracks that could have happened in the early universe. The way that they create gravitational waves is that they can form like kinks or cusps, or they can interact with themselves and form loops. So if a cosmic string is like floating around, it can, get confused and then form a loop, and then the loop pinches off from the string and then starts radiating gravitational waves. And the frequency of that really depends on the size of the loop. So if it makes a little loop or a bigger loop, it's going to be visible in different parts of the gravitational wave spectrum. And if enough of these loops exist and are radiating gravitational waves, that could add to the signal that we expect to see in pulsar timing array experiments. So we could actually detect these.
Okay, it was funny when you said that when they get confused, they form loops. But there are two things that jumped out at me. One, okay, you said they're long, but they're infinitesimally small. So I'm guessing you mean like their width is infinitesimally small. But you also described them as cracks, and maybe I missed it, but are they cracks in space-time, or what are they cracks in?
They're a phase transition. And so all I mean is like the ice cube cracking means it undergoes like this sudden phase transition that creates this dramatic effect. And here that dramatic effect comes from like this compounding of curvature in space-time that creates these defects, right? These deformities that are these cosmic strings.
But they're not matter per se.
You should try to talk to Edward Witten, and I think that he would give you a much better explanation of this. I don't think that you can think about them in matter in the traditional way. I mean, they have an energy density, and and so that energy you can relate to matter. But I think that the easiest way to conceive of them is to just be kind of like these, transparent threads of energy that are very dense, that can curve, space-time around them.
Okay. Well,
that's
very
how
cool.
I think about them like the like rice vermicelli, right? The transparent like glass noodles that are like floating around in space. And they have energy, which means that they can have mass or an equivalent mass. And they can interact with each other, and they can interact with themselves, and they can make gravitational waves. But I don't think that they would come from regular matter, right? Like, I don't think that they come from lots of hydrogen being compressed. I think that it's more of this, rapid transition of, cooling and things that happen in the early universe that would make space-time fabric like wrap in around itself. But you think you should ask someone else who's much more knowledgeable about cosmic strings than
Sure.
me.
I sense myself going down a Wikipedia rabbit hole.
Let me know what you find. I'd be interested to know.
But all right, at any rate, I feel like I threw pretty tangled up questions at you, and you did such an awesome job answering all of them in a really clear way. This was really an awesome conversation. So thanks so much for joining me, Chiara.
Awesome. Thank you. Coco Bean wants to say hi to the podcast.
Okay.
Come here, Snugglebell. Hi. Oh, she's just staring at me. I think she just wants a greenie.
All right. The podcat says hi to Coco Bean and goodbye to Coco Bean.
Coco loves cats. They don't love...
The NANOgrav 15-year dataset is about to be released next week on June 29th, which is when this will come out. And since I don't think we explicitly mentioned the name NANOgrav in the first part of this talk, maybe we can just start by saying quickly what the organization is and does.
So NANOgrav is a pulsar timing array experiment. And what we do is that we monitor about 68 millisecond pulsars. So these pulsars are nature's almost perfect clocks. In fact, they used to be better at keeping time than atomic clocks, but in 2012, atomic clocks got better. But basically, they can keep track of time up until about 100 nanoseconds over a decade. So they really are fabulous clocks. So it makes them perfect, natural gravitational wave detectors, since gravitational waves change the distances between objects. So if you're setting your watch by these pulsars and their pulses coming in, and then your signal started arriving early and then arriving late, it could be because there's a gravitational wave that's transiting through the galaxy that's changing the distances between objects. So the pulsars come a little bit closer and they get moved a little bit further away and then come closer again. And so your pulsar pulses arrive early and then late and then early. And this is a way of looking for these very low frequency gravitational waves. We believe that the source of these gravitational waves are supermassive black hole binary systems. But we're going to need a few more years of data to know concretely that that's what's sourcing these gravitational waves.
Mm-hmm. And so the new data suggests a few things, but first off, just what is the difference between this data and the data we had in the first part of this conversation? So what is new now that's being released?
So what's new in this new data set that just came out is the fact that there's now evidence for the full gravitational wave signature that we were looking for. So the previous data set had evidence for some amplitude of a gravitational wave background that's consistent with models that we created. However, we were missing part of the signal to know concretely that this signal comes from gravitational waves, and that was this Hellings and Downs curve. And so what that is that it's a distinctive shape that comes out when you cross-correlate all of the pulsar data. So briefly, what many of us that have done STEM degrees have had a whole bunch of data streams to analyze, and you're looking for something that's common in all of these data streams. And so each piece of data is going to have a small piece of signal, but a lot of noise. And the way that you get at the signal is by smashing together all of these different pieces of data and seeing like what the common thing is between them. Because every time you do this cross-correlation search, only the signal stands out. So the more data you have, the more signal you get and the less noise you get, because the signal is common and the noise is not common. So the more common signal you have, the stronger your detection will be. So in this data set, we have more pulsars with longer time spans. And so we've increased the signal, and now we can see this cross-correlation term in all of the pulsars. So we expect not only pulsars to have a common amplitude of the gravitational wave background that's manifesting in all of them, but they should also have a distinct correlation term that's a function only of the angle that separates the pulsars. So if pulsars are close together on the sky, they have a very strong correlation induced by the gravitational wave background. And as they separate, that correlation becomes weaker. Then they become anti-correlated, and then they become positively correlated again, because the nature of gravitational waves stretches and squashes space-time like this. So it can become, positively correlated, negatively correlated, and positively correlated again.
And so the major finding here now is that there is much firmer evidence for this gravitational wave background than there was before.
There's the first evidence ever that there's a gravitational wave background. Before, we had something that looked very interesting, but we needed to be really sure that what it was gravitational waves. And without having the cross-correlation terms between pulsar pairs, that might have been some sort of, dust or other kind of noise that was correlated between the pulsars. It would have been really unlikely, but it was still a possibility. So we had to be really, really sure that what we were seeing was gravitational waves. And now that we've seen this Hellings and Downs curve, or these cross-correlation terms, now we're really confident to say that what we found is definitely evidence for a gravitational wave background.
Sure. And I saw in one of the preprints that accompanies the data release that the signal also bears some relation or potential relation to other cosmological creatures and possibilities beyond the supermassive black hole binaries. In particular, I think some of the things that were mentioned were cosmic inflation, scalar-induced gravitational waves, first-order phase transitions, domain walls, and then cosmic strings. We actually talked about those in the first part of our episode, so we don't need to get into those again. But what credence do you have that this is all coming from supermassive black holes? And what are some of these other possibilities that I just mentioned? And how likely is it that they're contributing to this gravitational wave background?
Right. So right now I kind of feel like Mulder from the X-Files. I want to believe that it's all from
You want to believe in which one?
Holes. I want to believe it's all supermassive black holes. That would be super exciting. Some of the models that I came up with for the gravitational wave background based on supermassive black holes only predict the amplitude to be half of what we've measured. So it's super exciting that now we're learning something. We're learning that there's potentially more supermassive black hole binaries, that those are more massive than we thought that they were. Perhaps they merge more often than we thought that they did. So we can learn a ton of stuff from, comparing our theories to these measurements with the data. But it might not all be supermassive black holes. As you said, there's a whole slew of other cosmological sources of gravitational waves. And right now, the signature of all of those sources is very, very similar to the supermassive black hole signature. Those signatures manifest in how the amplitude of the background changes as a function of gravitational wave frequency. And right now, that change, there's a kind of slope of a line that joins together all of these different frequencies. And right now, all of those slopes are predicted to be about -1. For supermassive black holes, it's -2/3. For a primordial background, it's -1. And for cosmic strings, it's -7/8. And so right now, it's basically all -1 with big fat error bars. And so until those error bars come down, we won't really be able to tell what exactly is sourcing this gravitational wave background. We know that it exists and that any one of those sources can create this Hellings and Downs curve. But we're going to need some more years of data and more careful analysis to try to tease apart different contributions from different sources. And another source that we haven't talked about is, of course, intrinsic noise in the pulsars themselves. That might also be contributing a small part to this. We know for sure that that's not dominating our signal because we can see the Hellings and Downs curve. And that can only be made from gravitational waves. And this is also why we didn't proclaim evidence for the gravitational wave background beforehand, because we didn't have that part of the puzzle. We didn't see that part of the signal. But now that we do, we know that this amplitude that we've seen that goes together with the Hellings and Downs curve, we know that that has to be largely astrophysical or cosmological and not instrumental. But taking apart the signal that we've measured and really, now fine-tuning things to try to figure out exactly what's what is the next step.
And so quite broadly then, assuming that the source of the gravitational wave background is, as you want to believe for now, supermassive black holes, what does this new evidence then tell us about their nature or that of the universe in general? And I think in the first part of this conversation, we went into some of these possibilities in depth, but that's why I say so more broadly now.
Mm-hmm. So the first thing that we know now, if the source really is supermassive black holes, is that they merge. And this was a huge open question in the field before. Do supermassive black holes merge? In fact, there were some papers in the 80s which claimed that they didn't merge at all. And so it's really important to be able to say at a zeroth order level, supermassive black holes merge. And so that's also important for understanding how the universe works. Because if you go back to the beginning of the universe, we believe that, black holes seed in galaxies, galaxies merge, their supermassive black holes merge, and that, all of these galaxies grow by merging. And so a consequence of that is that their supermassive black hole should be merging. And some of those supermassive black holes are big enough to create this gravitational wave background. So it's this long sought after additional evidence that the universe works in this way, that, galaxies grow by merging with other galaxies. We've seen observational evidence through Hubble, the James Webb Space Telescope, lots of other different telescopes that you can actually see snapshots of galaxies in the process of merging. But this is the final piece of the puzzle that's been missing. Is what happens to the supermassive black holes. Do they hang out a few light years apart forever, never quite merging, or do they actually get together and grow through mergers?
And then lastly, two things that you've already touched on this a little bit, but one, what is the future of NANOgrav's research? And then what is the future of the theoreticians' parsing of that research?
So the future right now is everything. This is just the beginning of this new window of observation on the universe. With the evidence for the gravitational wave background that we have now, we expect to make a 5 sigma detection. Right now we have between 3 and 4 sigma. So 5 sigma is only a few years away, and we'll be able to make that, concrete detection.
Maybe we should say what the sigmas are for those who don't know.
Sure. So a 3 sigma detection has a false alarm probability of something like 1 in 1,000 years. So there's a chance of 1 in 1,000 that this is just a random configuration of data that looks a heck of a lot like a gravitational wave background. And so that's good enough for me. But in particle physics, they have much stricter definitions of what we call detection. And that's a whole other almost like philosophy of science conversation is, like, what would you believe? Because it really comes down to what different scientists believe in, like what their personal threshold for believing a detection is. So once we do have this stronger detection, which will come with a few more years of data and more pulsars, then we can start making maps of the gravitational wave background. And then we can start analyzing those maps and looking for, weird and wonderful things. And this is where the theorists can really go crazy, right? Like, what happens if you look at a map of the gravitational wave background and you see a hotspot of gravitational waves, and then you look at that part of the sky with your telescope and there's no galaxies there, right? So what on earth is that? Do you have like rogue supermassive black holes, or is it some sort of weird cosmic string event coming from that part of the universe? Like, these are all questions that I think we're going to have to take really seriously. And this is where the theoreticians really, start turning things up to 11. We get to get really, really creative with different models of gravitational wave emission in the universe and what could be sourcing this background and also what's next.
So this is really just like a huge moment in our understanding of the universe, and things are going to blow up from here.
It's a supermassive moment.
Well, that is awesome. Chiara, it's so cool to be at the cutting edge of astrophysics today. So thanks so much for doing this addendum to our initial conversation with me.
It's my pleasure. Thank you so much.
Hold on, geeslings. Before you go, please like, subscribe, follow if you haven't already. Smash all those buttons. And also, if you haven't followed me on Twitter at Robinson Earhart, or if you're not joining me every morning as I eat my pint of ice cream on Twitch at Robinson Earhart on Robinson Eats, please do so.